So now we're going to start to take our first steps toward constructing the Jacobian for more complicated mechanisms. To do this, we have to understand how angular velocities and rotations interact with each other. So assume we have an axis omega, and our rigid body is rotating about this axis. What you can picture is that as the rigid body rotates about this axis, infinitely many circles are being generated by the points on this rigid body, and these circles are in a plane that are perpendicular to our omega axis. The rigid body has an angular velocity. Here, we're denoting our angular velocity omega as a scalar theta dot times the unit vector k that points along this angular velocity omega that we defined in the previous slide. It's also worth noting that the points on the rigid body themselves have a translational velocity as a result of the angular velocity of the rigid body. That angular velocity causes a translational velocity through this cross-product relationship that we learned about in physics. So we take our vector omega, we find an origin that's on the vector omega. The vector that points to the point P, we'll call that vector r. Omega, the angular velocity cross this distance r, is the translational velocity of this point P as a result of the angular velocity omega of the rigid body. So the question is, theta dot, when we had k theta dot equals omega, is theta dot enough to represent the angular velocity or the rotational motion of this rigid body? So really the question I'm asking is, what do we do when we go into higher dimensions? So let's take a look at the derivative of a rotation matrix. R dot is simply d by dt of r of t. And what we want to do now is we want to see what does this derivative look like and how is it related to angular velocity. So now to compute the derivative of a rotation matrix, we're going to show that its derivative is equal to a time-varying skew-symmetric matrix times the rotation matrix. This is actually something that's rather straightforward to show. What we do is we start with the basic property of an orthogonal matrix that R transpose is equal to the identity element. We're now going to take the derivative of both sides. Remember, it's the derivative of the first times the second plus the first times the derivative of the second. The derivative of a constant is 0. And when you look at this expression, you can sort of see that this guy here is the transpose of this guy here. So if we bring this to the other side, we're going to have a nice skew-symmetric relationship. Let's see how this works. Let's substitute lambda for minus r dot. So over here, this becomes a negative lambda of t. We're going to bring lambda of t to the other side of the equation, and then we're going to post-multiply by r, because remember, r transpose the identity element. When we post-multiply the lambda by r, we end up with lambda r. So we end up with r dot is indeed equal to lambda times r of t. And now we'll show that lambda is indeed a skew-symmetric matrix. So we start with this expression over here that we got from differentiating this term. This becomes a negative lambda transpose. This becomes a negative lambda. We bring the lambda to the other side, and you see that negative lambda transpose equals lambda, a skew-symmetric matrix. Now that we've shown the derivative of a rotation matrix is a skew-symmetric matrix times that rotation matrix, what we want to show is that the skew-symmetric matrix is actually a function of the angular velocity of the motion that the rigid body is experiencing. So let's suppose we have a fixed frame, frame 0, and we have a moving frame, frame 1. Frame 1 is rigidly attached to this rigid body. We'll put a point P on this rigid body. Let's look at the motion of P. The derivative of P dot 0 is simply the derivative of R01 P1. Remember, P0 is R01 P1, so P0 dot is d by dt of R01 P1. When we take this derivative, remember, it's the derivative of the first times the second, the first times the derivative of the second. It's worth noting that P1 dot, the velocity of the point P in frame 1 is always going to be 0 because P, this is a rigid body. P is always the same distance away from the frame that's usually attached to this rigid body. So this goes to 0. The result is R01 dot P1. Now what we'll do is we'll substitute in what we derived before into this expression. Now we have a skew symmetric matrix R01 times P1. Now what we're going to do is use the properties of that relate angular and translational velocity together. Remember, V is equal to omega cross P. So let's look. P1 dot is going to be equal to omega cross P0 using this property here. P0 is simply R01 P1 through the simple transformations that we learned early in the semester. Now we're going to take this equation and equate it to this guy because P0 dot is the same thing as P0 dot. And now we can show that this line is equal to this line because P0 dot is the same thing as P0 dot. In other words, this is equal to that, this is equal to that. And now we get to use the properties of skew-symmetric matrices to show that a skew-symmetric matrix times a vector is the same thing as the cross product of that vector by the vector which defined the skew-symmetric matrix in the first place. And that tells us that our skew-symmetric matrix is a function of the angular velocity of our system. So let's see if all this analysis works for a very simple case. We want to compute the angular velocity vector for rotation around the x-axis. So we know that the derivative of our orthogonal matrix is equal to a skew-symmetric matrix times the rotation matrix. We'll rearrange terms. Here's the skew-symmetric matrix because now we're hunting for the angular velocity vector. So skew-symmetric matrix, which encodes our angular velocity, is derivative of r times r transpose. Here is the derivative of r. Don't forget the chain rule. And then r transpose, that's pretty easy to figure out. When we multiply these out, you'll see very quickly our skew-symmetric matrix has only a 1 and a negative 1 term inside of it, which means that the angular velocity vector, no surprise, is just rotation around the x-axis. Again, we then are able to show that the derivative of our rotation matrix around the x-axis is simply the skew-symmetric matrix we form from an angular velocity vector around the x-axis times rotation around the x-axis.